We saw zero-order empirical entropy, and we talked about the relationship between zero-order empirical entropy and the Shannon entropy of a memoryless source. But we don't have to stick to memorylessness. Let's see what happens if we do include a little bit of memory. Because, after all, we know that zero-order empirical entropy is not really going to be sufficient in real-world situations. Like if we're analyzing human text, we know there's a predictability to human text. Like we know that certain pairs of letters are going to tend to appear together, or certain pairs of words are going to tend to appear together. And there's nothing special about pairs, right? There might be strings of letters and strings of words. We know, for example, that the word the is very frequent, and therefore it should not be too surprising that if you look at a large corpus of data, of English language data, you see lots of THs and lots of HEs among the different combinations of two letters, right? We know context matters, and therefore there should be a way to use context and maybe salvage some of what we learned about zero-order empirical entropy and codes for exploiting zero-order entropy. There should be a way to use context to get better codes. So that's what this lecture is about. So we ought to be able to compress better if we consider the surrounding context. And the way this would impact our way of doing things where we build codes, we build code books consisting of different codes for different symbols, is we're going to just let the codes change depending on the context. Okay, so we're going to let the code book C change depending on the surrounding symbols. Okay, so what do I mean by that? Let's look at what you have to imagine is like a big long DNA string. Imagine it's going way off in either direction. And I've highlighted the A's in red, and I've highlighted the right context for the A's in blue. Specifically, I've highlighted so here are the A's. I've just highlighted in blue the 3 characters that are directly to the right of each occurrence of A. As we'll say in a moment, there's nothing special about whether the context is to the right or to the left, right? We could consider it either way. All right. So I've got my A's, A, and I've got my right context, TCG, GCG, and here's TCG again, and here's TCG again, and here's TCT. All right. The idea is we're actually going to have different codes for different contexts. So, right, so for K symbols of context, where in this example we're using K equals 3, we have a set of codes that we might denote as a bunch of big C sub i's, each of them taken from, each of them being a code with a subscript, a specific subscript, which is a length K context. Okay, so in this example here, looking at our first A, that might use the code book for the right context, TCG, right? If the right context is TCG. So we use the TCG code, right? Big C subscript TCG of A would be the code that we would use. Kind of like before, whereas before we would just say C of A. There was just one code all the time. Now the code depends on the context. So that context I'm putting here in the subscript of the code. Likewise, for the second A, we would use the GCG code. And so on. So actually, in this particular example, there's 3 places where we would reuse that same TCG codebook because A had the same right context in those 3 cases. Okay, like we said, we can consider the context to the right, as in this picture. We could also consider the context to the left. We could do either. There will be some reason to prefer thinking of context to the right when we talk in terms of the Burrows-Wheeler transform, but that's just not so important for today. We could do it either way. Another thing you'll notice about these examples is that I designed them so that these contexts didn't bump into any other occurrences of A, But it would be perfectly fine if they did, right? If these were closer together such that this A and this A were only 1 or 2 characters apart, that would be fine, right? The right context for the first A would include an A in it, but there's no big deal there. Okay, so we are going to have a separate code for separate possible contexts. Now that we know that we're going to have a separate code for each separate context, we're still left with the question of how do we pick the code? Okay, so how do we build each of these codes? C sub sigma to the k. Sigma is the alphabet, right? So sigma to the k is all possible contexts of length k. And the answer is going to be, we're going to do it exactly the same as before, right? But by first conditioning on the context, right? We're just going to take what are all the characters in my string that have a particular context, right? It might be like CTG to the right, or it might be AAA to the left. But I'm going to take all the characters that have a particular context and then consider those characters to be concatenated to make a new string, then apply a normal coder, a zero-order coder, something like a Huffman code. Right? So the idea is, same as before, but the frequencies are now conditioned on context. So for example, the code GCA is considering just the number of times each symbol occurs just after, let's say we're using left context, just after an occurrence of the string GCA. Okay, so we've really just taken the high order empirical entropy scenario and kind of by first stratifying by context or conditioning on context, I'll say it either way, and then saying we're just going to use a normal zero order code for everything that has the same context. We've turned the zero order problem into a sort of two-level hierarchy where first we have to figure out the context, then we can apply our zero order code. Okay? So let's take an example. Here I've got abracadabra. And I've highlighted the A's because what I would like to do is make the code book, the code for characters that have A to the left. Right? So the context that I'm considering right now is the context of having A to the left. Okay? So just like we said, if we're conditioning on that context, then what we need to do is we need to take all the characters from this string that have A to the left and make a new string out of just those. Right? So in this example, I've highlighted them already. What are the characters that have A as their left context? B, C, D, B. Now be careful, I wrote A in red here, but that A has A as its left context, so I need that one too. B, C, D, B. Okay, so those are the ones. So I'm going to build a new string called S sub A, which will just consist of the characters that we get by concatenating the characters that have A to the left. And so we know what that's going to be in this example. So let's say S to the A equals, and we're going to take all these green characters, right? B, C, D, B, and then that A, even though it's red, B, C, D, B. Okay? It's just these characters. Okay? Right, so there it is. And then what do we do next? That's the string that consists of all the characters that have A as their left context. All we're going to do is build a usual zero order code based on the frequencies of the characters in S sub A. Right, so let's look in S sub A and let's just make our usual sort of frequency histogram of the different characters. So A occurs once, B occurs 4 times, C occurs twice, D occurs twice, and R is one of the characters in the original string, but it just so happens that there are no R's that have A as their right context, so this one's actually going to be 0. Okay, so that's our frequency. That's our set of frequencies that we could use to hand off to Huffman, for example. And the fact that R doesn't occur at all, like there are no R's that have A as the right context, well, that essentially means that R won't get a code, right? We don't really need Huffman to assign a code to R, so it'll be excluded. Okay, so let's do it. Let's build a Huffman code for these characters and their frequencies. Okay, so here's the trivial set of leaves of what will become the Huffman tree. Let's do one round of merging. Well, I'm going to take the two nodes that have the lowest sum of their weights. So I actually have two choices. I could pair A with D or I could pair A with C, but let's, for simplicity of the picture, let's pair A with D. Get a new node. Here it's going to have 3 as its weight. Okay, there we go. All right, next round, what am I going to do? I'm going to combine the 3 and the 2 to get a new node. It's going to have 5 as its weight. Last round, I'm going to combine these two, get a node that has 9 as its weight. Okay, let's take away the weights. Remember, the next thing we need to do is label the edges with the edges that go down to the left as getting 0s and the edges that go down to the right as getting 1s. So we'll put 0, 0, 0, 1, 1, 1. And now we can write down our codes. So I'm going to call this C subscript A of A. What's the code for A when my left context is A? And it's dictated by this Huffman tree. So it's this path, so it's just 0, 0, 0. We can do the same thing for D, which has code 0, 0, 1. So C subscript A of D equals 0, 0, 1. Now C has code 0, 1. C subscript A of C equals 0, 1. And B, the most frequent, has code 1. C subscript A, B has code 1. Right? I have the subscript A in each of these cases. That's denoting that this is the code conditioned on having A to the left. Okay? All right, so now let's create the entire code for a particular example. And we'll just use a context of 1 so that it doesn't take us too long. And so let's look at a new string. This is just Mississippi twice. Okay? And we're going to go by left context, one character of left context. So we're going to stratify by left context, just taking one character to the left. And so let's start off by constructing our string big S sub I. In other words, this is the concatenation of all the characters that have I as their left context. So which characters are those? S, S, P, M, S, S, P. Okay? S, S, P, M, S, S, P. Okay? And so the frequency vector associated with that is going to be, well, S occurs 4 times, let's do P next. P occurs twice, M occurs once. Okay, so there's my frequency vector. And if I go ahead and do Huffman, I'll end up with a code that looks like this. C of I of P is O, C of I of M is O1, C of I of S, the most frequent one, is 1. Okay, nice prefix-free code for the characters that have I as their left context. Let's keep going. So now we did the characters that have I as their left context. Let's next do the characters that have M as their left context. I'm just going to read them off. That's I. That's it. There's only 2 M's, and they both have I's to the right. Okay, so the frequency vector here is obviously trivial. I just occurs twice. And what do we do here? There's no code, right? There's no need for a code here. We know that M is always, if you see an M, you know that there's an I to the right. There's essentially just no code. Okay. All right, so that was I and that was M. Let's do P next. S sub P. Okay, let's see. Okay, so we got a P, an I, and a P and an I. So it's going to be PI, PI. Okay, nice trivial frequency vector. Can have a nice trivial code here as well. So let's just say C subscript P for P is 0 and C subscript P for I is 1. Doesn't matter which gets 0, which gets 1. There's only 2 characters here, so it's a trivial code book. And finally, let's do S. So which are the characters that have S as their left context? SI, 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 SI. Okay? SI, 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 SI. Another simple frequency vector. Another simple set of codes. So C sub S be 0. C sub S sub I be 1. Okay? So those individual codes are pretty simple, which stands to reason because once we condition on the context, not only is it a smaller set of characters we're now worried about since we've conditioned on some context, but we have created a somewhat more homogeneous set of characters, right? It's a more predictable set of characters because it's just the ones that have a particular left context, right? And as we say, some character pairs are going to be more likely than others, right? There's a certain association between vowels and consonants where you sort of would expect vowels or pairs of vowels to have a consonant before them. And there's the word the, right? So you tend to see a T before an H and things like this. So overall, if we pictured all the codes that we've written all on this slide, right? The code for the left context of I, code for left context of M, P, S. We could picture it sort of as a tree, and indeed we could picture the whole approach as kind of like a tree, where the first level of the tree is pick your context, and then the next level of the tree is, okay, here's your code. Given that context, here's the code you should be using. Okay? So not only is our strategy, not only is our method kind of tree-shaped in this way, but we could say that the definition of high-order empirical entropy, which we're going to call H subscript K, right? H subscript 0 was zero-order empirical entropy. Now we've gone to this more general notion of kth order or high-order empirical entropy or kth order empirical entropy, which we'll call H sub K. And the definition itself is also kind of hierarchical. It's going to have, as we'll see, it's going to essentially be a weighted sum where these are the terms of the sum, and the thing that we actually have to add up is related to the zero-order entropy in each of the nodes in the second level. Okay, so let's write down the definition of high-order empirical entropy, H sub K. So H sub K of a length n string S is a weighted sum over all contexts, all possible contexts, of the zero-order empirical entropy of the symbols having that context. So let's write it out in symbols. H sub K of S is the length n string, equals, and then we have a sum here, okay? Over all contexts is in blue, so let me use blue to write what the sum is a sum over. It's a sum over, I'm going to use T as a variable for a string. So all possible strings in the set sigma to the K, right? K here, K here. All right. I should note that there's two sigmas here, right? So this sigma is just a sum, right? So this is just sum, right? Whereas this sigma down here is the alphabet sigma, right? That's the sigma for all the set of symbols in the alphabet. Okay, so all we're doing here is we're summing over all possible length k strings from the alphabet. Okay, we say it's a weighted sum, so let's now write down the weight, which is going to be a fraction. The numerator is going to be the number of characters that have that context, right? So it's going to be the length of S sub t. Remember what S sub t is. It's just all the characters that have that context t concatenated together. Okay? Over the total number of characters n, and then times the zero-order empirical entropy of those characters, the S sub t. Okay, so the kth order empirical entropy of a string is a weighted sum where the weights are how many characters, what's the proportion of characters that have that context, and then times the zero order empirical entropy of the characters that have that context. Okay? So remember the bit of notation, which I used previously, and then I'm using again here, which is that S with a subscript is a concatenation of all the characters in the string S that have the subscript T. Okay? So with this high order empirical entropy notion and with our strategy for implementing a high order coder, we can achieve a bound a lot like we said we could achieve with Huffman coding. So we can compress a string to, at most, n times the kth order empirical entropy of the string plus 1 bits. Okay? Just like we said before with Huffman coding and the zero order empirical entropy, except for that we had a 0 down here. That was the zero order empirical entropy in the expression. Now we can compress down to the k order empirical entropy, right? And increasing k is only going to reduce that empirical entropy, right? Because the more context we consider, the more predictable the next character is going to be. Okay? But it comes at a cost, obviously, right? This picture, just having one zero order code from Huffman, for example, would be incredibly simple and incredibly easy to use and nice and compact, right? We would really just need to store the code book. We'd need to store the symbol of the what bit string we're going to use for each symbol. Whereas here, what we're suggesting is we might have many codes, right? For large k, right? K, the number of possible contexts is increasing exponentially with k, right? So for high enough k, we might suddenly have an enormous collection of codes, and just the overhead of switching, the overhead of storing it and the overhead of switching between them, this might start to add up and get very costly. So it's not as though this is a panacea, right? Higher k is not necessarily better, but k is flexible. We can pick k, so we might pick k to be a nice computationally reasonable value, but that nonetheless provides a substantial improvement over zero order empirical entropy. Okay, so this high order empirical entropy encoding idea, where we first condition on or stratify by context, then we apply a nice simple zero order code to all the characters that have that context. It's like we're reaching into the string and we're extracting some of the structure that we need in order to compress well. Okay? And then this value k, which we can adjust, is balancing compression with overhead. More compression for higher k, but also higher overhead. The principle at play here, thinking back to grouping versus ordering as kind of the two basic principles, it's a little bit more like a grouping principle, right? We're taking the characters that have the same context as a group and then encoding just that group, right? So, and the way we pictured it as this tree where the edges leaving the root node of that tree are just labeled with different contexts, right? So this is a kind of a grouping principle-based idea. Whereas the zero-order empirical entropy-based methods are simpler, faster, they require less memory. It's just that they can't really find as much structure as the kth-order empirical entropy. They're not trying as hard to reach into the string to extract the structure that would be needed to get that increased predictability. Or can they? Right? This is foreshadowing, right? It could be, actually, if we're clever enough about what order the characters of the string are in, then it could be that zero-order empirical entropy can kind of reveal a lot of what we need, right? Order to the rescue. It's not at all obvious what I might mean by this yet, but as we'll see later when we talk about the Burrows-Wheeler transform, the ordering that's induced by the Burrows-Wheeler transform combines in a nice way with the zero-order empirical entropy to also give us a way of revealing more structure in the string and getting more predictability. We'll see that soon.